All right, so let's start. Today we're going to solve our first problem based on the stress-based solution approach. Okay, so the example is the spinning beam. Now, so when you look at this example, if you want to relate to it, right, for the spinning disk, you can think of a CD-ROM. It was plane stress. In this case, as we emphasized before, we're going to work in a unified framework for intrinsically 2D problems. So it could be plane stress or strain. But if you like, think of a helicopter blade. Okay, when I draw this example as something physical that we can relate to. Well, it's a beam, so I'm going to draw a rectangle. Okay. These will be our in-plane dimensions, x1 and x2. So the length of the blade is 2a, and the height is 2b. So that's how it looks. And it rotates. Now, you should be careful. So in the spinning disk problem, if we viewed the problem from above along the axis of rotation, we would have seen a disk. So in this case, we're seeing a rectangle. So it looks a little bit suspicious eventually when I saw the numerical examples as well. It looks very much like even the numerical solution, a tiny bit at least visually. It's as though this disk is like this and we're viewing it from the side. No, this is a beam. So it's a rectangle. So if you like, the thickness direction doesn't really matter because this could be a plane stress or strain case. But if you like, this is the thickness direction. I don't want to complicate the drawing, okay? But it could be very thin, for instance, if it's plane stress, or it could be plane strain, and then we don't care about the thickness. And under those ideal scenarios, we're essentially taking a cut along the thickness direction, and this black rectangle indicates that cut. And it really doesn't matter at which point along the thickness direction that cut is located if we're in an ideal plane strain or plane stress scenario. Okay? So this is the way the rectangle is rotating, right? And these are coordinate systems. This is a coordinate system, if you like, that also rotates with the blade. Okay? And at this instance, this is the orientation of the blade that we're trying to analyze. All right, so the original setup of the problem is there is no body force, and because it rotates, there is an acceleration. The acceleration is something we already know in the cylindrical coordinate system. It's minus omega, the radial speed, omega squared r. But in Cartesian coordinate system, it needs to be reformulated. So it has a x1 and a x2 component. Okay, so this is the acceleration, and because unfortunately I'm using the symbol omega a lot, and before I called the radial, I'm sorry, I say radial, angular speed omega. Now I'm going to call it omega naught because eventually omega is going to appear as a parameter that indicates whether we're in a plane stress or strain scenario. So omega naught is our angular velocity. Okay, so that's the original setting. But in our formulation so far, what we did was we omitted the acceleration, but we admitted the presence of a body force. So I'm going to take this term, essentially throw it to the left-hand side of our equilibrium equation and formulate it as a body force, which is something I had commented on before as we were analyzing the spinning disk problem. It really doesn't matter whether this is physically an acceleration or a body force. In the PDE, in the equilibrium equation, it appears in the same way. And therefore, I'm going to say that I have an F1, which is minus, right? I'm putting it to the left-hand side of the equilibrium. So minus, so it's this term times rho, the density. That's along the one direction. And then along the two direction, we have rho omega naught squared x2. So we admit that there is a body force and there is no acceleration. Remember, F3 is equal to 0, and I'm only monitoring in-plane components. So this here is our setting. Okay? Our setting for intrinsically 2D problems in the context of the air stress function. So in that case, what we need is the potential that delivers the body force. So remember that we defined the potential capital omega to be such that when I take its gradient, it delivers the corresponding component of the force through a minus sign. So since this is the force that I have, then I can find out easily that the potential that delivers these forces is 1/2 rho omega naught squared x1 squared x2 squared. Right? So if I take the derivative of this with respect to 1, so I get minus rho omega naught squared x1 with a minus sign, that term. Likewise for F2. Okay? So that's the potential, and we will need that potential. And also notice that the angular velocity goes as a square into our equation, so it really doesn't matter whether it rotates like this or like that. So greater than 0 or less than 0 doesn't matter. Although I've drawn the direction of rotation according to the right-hand rule. Okay, so now what we're going to do, remember, is that we are going to start with, so the diagram, solution diagram for the stress-based approach is you propose a form for the stress field that a priori satisfies equilibrium. And we're not going to do it directly in terms of sigma. Now we know that what we really propose is not sigma, but rather an air stress function. So the stress is a function, or is derivable from the air stress function. So first we're going to propose, and once we formulate the thing in terms of the air stress function, this thing automatically satisfies equilibrium. So we don't have to worry about that. It's a priori satisfied. So I'm going to first propose a form for phi that is problem tailored. I'm going to look at my problem, and first I'm going to propose the simplest possible phi, and then I will enforce compatibility. Okay. And when I enforce compatibility, that form that I have proposed will be further restrained. And by additionally imposing the boundary conditions on the problem, I will be able to find the constants that appear in phi and hence solve my problem. And since I have restrained the form of phi through compatibility, I know that there exists a displacement field. So as a byproduct, if necessary, I can go ahead and construct that displacement field as well. So that's what I'm going to demonstrate this lecture in detail. So the first thing we notice is that in this problem, right, suppose you were trying to use a displacement-based approach. In a displacement-based approach, we like to have some symmetry, like cylindrical, spherical usually. So I look at the problem. There really is, negligible. I mean, there is, okay, some symmetry in the problem, but nothing that I can simplify with towards a cylindrical or coordinate, spherical one, obviously. So I'm stuck with a Cartesian coordinate system, right? So there is no geometric symmetry to simplify, right, our displacement. So it's hard to say or come up with a simple form, as in, let's say, in the simplest case for the pressurized thick-walled sphere. It's hard to come up with a form for U alpha that we think is a good solution. It's really hard to say anything about it at this stage. So it's tough, let's say, for a displacement-based approach. This problem is tough for such an approach. Okay. Right. Now, we do have a 2D problem. Let me also make that remark, and we're going to come back to this remark. So we have a 2D. It could be a plane stress or strain problem. Right. So we are already omitting the thickness direction, but let's say it's plane stress. So ideally, that case is achieved when the thickness is very, very thin, right? But there is a height and there is a length, okay, or a width. So it's 2D. But now imagine additionally that the height is very small, okay? So then the problem, you're omitting the third direction, as it becomes very, very thin, and you notice that we have eventually stress-free upper and lower boundary conditions here, right? Traction-free. Also, the left and right edges are also traction-free. Eventually, we're going to make use of those facts. But since these two surfaces are traction-free, if it becomes very, very thin, you can imagine that it's also going to be plane stress along the two direction. So you can omit the two direction as well in some sense, and you're only left with variations along the x1 direction. So now it will be like a rod rotating. Okay, that's what it's going to be. So it's 2D, but eventually if we make it thinner, then it's an intrinsically 1D problem, but we don't have to do anything special for that. We will automatically capture it. So nevertheless, if B over A goes to 0, then it would be a 1D problem. And that's like, let's call it the spinning rod. Of course, if you invoke that it's 1D from the outset, it would be easier to solve the problem. That would be one advantage to directly go for that scenario, but our solution will be able to capture that limit. So I'll come back to this remark as well, B over A going to 0, because it turns out in this problem, we won't be able to find the exact solution except in a very, very specific scenario. And we will have to eventually make an observation that is somehow related to this ratio B over A. Okay? But I've already, in my problem, in my diagram, or the schematic of the problem, I've already drawn everything suggestively. So in my analysis, I want the x1 coordinate to be aligned with the longer direction. And the x2 direction is aligned with the shorter direction. That's conceptually what I like to have. Okay. And one direction is much, well, somewhat larger than the other direction. So we're in good shape. So we have made a few observations. So now we know that the starting point is to come up with a problem-tailored form for the area stress function. That was the concept. So our first approach in a displacement-based setting would be to say something about the displacement. And now our approach is to say something about the area stress function. And there are two particular things that I'd like to remark. The first one is that so I have a beam. It's rotating rapidly. So under the influence of those inertial forces, it will try to expand, right? And some stresses will occur throughout the structure. Now, stresses will certainly occur, right? And moreover, stresses at the, for instance, sigma 2, on the plane with normal 2 in the direction 2. It's traction free. Here it's 0. And here, it's not 0. So that means the stress is going to vary, right? So stress is not a constant. That's an immediate observation we can make. It's a very simple observation, but it is immensely helpful. So stress equals 0 near edges. Now, I have to say this carefully, of course. When I say stress is 0, for instance, on the upper surface, I'm talking about sigma 2. On the right surface, I'm talking about sigma 1. For instance, but let's just briefly summarize the observation like this. Stress is 0 near the edges and non-zero in the middle. Okay, so Now, then we recall the very last exercise that we did. And I remember that if I have quadratic terms in phi, the stress is associated with the second derivatives of phi. So if I have quadratic terms in phi, the stress comes out to be a constant, okay, as it is invoked by the area stress function. And I know it's not a constant. It must vary. So the area stress function must have terms that are higher than quadratic. That is my first observation as a result of non-constant stresses. Okay, so phi, the area stress function, must have terms greater than quadratic. So if it has cubic terms, I will have linear variations of the stresses with respect to coordinates. And if I have quartic terms, eventually I will have quadratic variations, etc. Now then I make a second observation. And the observation is, this one is also rather simple and we can relate to. For instance, the beam tries to expand. And for instance, at this point, there will be a certain sigma 1,1. Okay? Now, if I look at the symmetric counterpart of that point, because this thing is trying to expand, you can think of x1 equals 0 and x2 equals 0 lines as symmetry lines. And in particular, for instance, sigma 1,1 here and sigma 1,1 there should be the same. Okay, does that make sense? Right? Because this thing is trying to expand, the profile here will be the same as the profile there. So the stress will be symmetric. Likewise for sigma 2,2. Okay? So I know that the stresses will have a certain symmetry with respect to the coordinates. Okay? So in particular, so I'm going to call that stress symmetry. And so let's highlight these two important observations. The first one is that I must have at least cubic terms. And the second one is symmetry. So for instance, normal stresses are even functions of coordinates. So an even function, remember, means that, for instance, if I'm looking at sigma 1,1 and I'm looking at minus x1, x2, that should be equal to sigma 1,1 plus x1, x2. So it doesn't matter whether you're in the well, really what I wanted to say was perhaps like this. It doesn't matter whether with respect to x2 equals 0, I'm above or below the coordinate axis. The value of the stress will be the same, and that indicates that the stress sigma 1,1 is an even function, for instance, of x2, likewise of x1, etc. So now, since that is the case, that further restricts the form of the area stress function. Okay? So the stress must be an even function of phi. So if I have cubic terms in terms of coordinates, it won't be an even function. So I must have no cubic terms. I must have at least in the area stress function to the power of 4 or quartic terms. Okay? If I take two derivatives, I will have stress terms that are quadratic in the coordinates, and that is an even function. So finally, then I can say that the simplest form is phi. Okay, so now I'm going to go ahead and put these two observations together. And I'm going to propose the following area stress function. So in fact, let me go ahead now and also so that we can see the implications of these two observations more clearly, let me now go to the next step immediately. Remember, for instance, in the displacement approach, based approach, first I propose some form for the displacement, simplified with respect to the coordinate dependence, and then I go ahead, calculate the strain, etc. So in this case, I start with the area stress function, and now the next natural step is to calculate actually what the stress is. And that's important because eventually I need to impose boundary conditions. So first, I can calculate sigma 11. Let me do this with a different color so so it stands out a little bit. It's a little bit cluttered. So sigma 11 is equal to, again, this is nothing to memorize or remember, but we need to understand individual terms and how they eventually contribute. So that's the expression for sigma 11. Sigma 22 is phi comma 11 omega, and sigma 12 is minus phi comma 12. Okay? So those were the expressions for the stress components that we proposed last time. So I can go ahead. I have the area stress function. I can take derivatives. So with respect to 2, I have, so this has to be a square. I don't know why I wrote 1. Okay, so let's go ahead and take two derivatives with respect to x2. So I have 2a2 x1 squared plus 12a3 x2 squared and plus 2a5. Okay? Plus omega. Don't forget the body force. So minus 1/2 rho omega naught squared x1 squared plus x2 squared. So that's sigma 11. Okay, sigma 22 phi comma 11. So I have 12a1 x1 squared plus 2a2 x2 squared plus 2a4 minus 1/2 rho omega naught squared. And finally, minus phi comma 12. This term dies, that term dies, these two die, so I only have that term, right? So it's minus 4a2 x1 x2. Okay, so I must have at least cubic terms. Okay, so I have, for instance, yes, I have quadratic. Remember, we're not interested with terms that are linear or constants. We already argued that since stresses are associated with second derivatives, I'm not interested in any constant term or linear term anyway. So the least we start with is quadratics. I have the quadratics, but quadratics lead to a constant stress field. In particular, they deliver these two terms. Okay? But I know that my stress field is not a constant, so I have to have terms that are larger than quadratic. But then the stress displays a certain form of symmetry, so eventually I don't want cubic terms in the stress because that would violate this type of a symmetry. For instance, it would be an odd function. So I don't throw in any cubics. I throw terms that are associated with power 4. Okay? So that's the idea, based on these two simple observations. Okay, so this, notice that it is the simplest possible form. Okay, so I'm throwing in the simplest. I have symmetry and I have non-constant stress field, right? But you should realize that it is perhaps not the best. And I will come back to this point shortly. All right. So in particular, you might ask yourselves, well, why not add, let's say, a term that is, let's say, x1 to the power 6, okay? Because x1 to the power 6 would lead to x1 to the power 4 type of term in sigma 11. And that is also not constant. That also displays even symmetry. So why not? But we're going for the simplest possible form presently. That's why I have omitted that term. I'm just trying to address these two items there. Now, one more thing that I'd like to highlight at this point, just to draw your attention, because we'll come back to this form and keep taking derivatives. Eventually, we will see that this term will vanish. So let's make a note of it here, so that when we take derivatives, we can immediately get rid of it, okay? But I'm going to show you now why it vanishes. All right, so let's proceed with now the determination of those constants. Now, what next comes in our solution diagram is really compatibility. Now I have some problem-tailored form, right? Problem-tailored in the sense that I'm looking at these two observations and trying to satisfy them with the simplest possible form. Perhaps not the best, but we'll see what the shortcomings are, if there are any. Now, the next approach is to constrain that form further. In other words, I'm going to ask myself, is there possibly some constraint on these constants A1 through A5? Because, of course, this area stress function must be satisfying compatibility. That will be the next natural thing to impose. But it turns out that sometimes it is better to simplify that form a little bit by first looking at the boundary conditions, because I know what the stresses are at these functionally. So I can say something about those constants by looking at the boundary conditions. And the boundary conditions are, for instance, at this point, sigma 2,2 is equal to 0. Along this line, sigma 1,1 is equal to 0, okay? And also, both here and there, sigma 1,2 is also equal to 0 because they are all traction-free boundary conditions, okay? So I'm going to make use of that first. So before, let's say, enforcing, let's simplify phi a little bit, okay? And then the first thing that I will go for is the simplest one. Functionally, sigma 1,2 is just a constant times 2 coordinates. So on the top surface, which is where x2 is equal to plus, or, well, also the bottom surface, minus b, sigma 1,2 is equal to 0. So that's my first boundary condition. Let's call this condition 1, okay? So for instance, if I go for the top surface, right, I have minus 4 a2 x1. I would have a plus b, and if I go for the bottom surface, it's a minus b. But really, it doesn't matter. In either case, it should be equal to 0. And if this is supposed to be equal to 0 for every point along the top or bottom surface, so in other words, irrespective of x1, clearly a2 has to be equal to 0. And hence, that term will vanish. Okay, so a2 is equal to 0. Done. Okay, so that's my conclusion number 1. Let's go to conclusion number 2. So I can look at also sigma 2,2 at the top or bottom surface. Let's call this condition 2. And sigma 2,2 then has the form, right? 12a1 x1 squared plus 2, well, okay. So now I can go ahead and drop these terms. So a2 will never be there. A2 will never be there. And this has died, right? So I can remind myself, because as I said, I'm going to be taking a lot of derivatives. So that term is not there. So I have then 2a4 minus 1/2 rho omega naught squared x1 squared plus b squared. That should be equal to 0. Okay, so plus or minus b doesn't matter. Okay, so then I can collect terms here. So 12a1, right? There is an x1 squared factor likewise here, minus 1/2 rho omega naught squared x1 squared, and then plus 2a4 minus 1/2 rho omega naught squared b squared equals 0. right? No mistakes. Okay. So just like here, for every choice of x1, this thing had to vanish, and therefore a2 had to be 0. For every choice of x1, likewise, along the top or bottom surface, this has to be equal to 0, which means both that and that, they have to identically vanish. Okay, so from this one, I find that a1 is equal to 1 over 24 rho omega naught squared. Okay, and from the second one, I find that a4 is equal to 1 over 4 rho omega naught squared b squared. Okay, so now I'm going to go for the last one, sigma 1, 1. Sigma 1, 1 has to be 0, not at the top and bottom surfaces, but on the left and right surfaces. That's where I have traction-free boundary conditions. Notice that sigma 1, 2 also has to vanish at the left and bottom, at the left and right edges. But since I already found out that sigma 1, 2 is 0, I don't have to worry about it anymore. Okay, so sigma 1, 1 at x1 equals plus minus a. And this is going to be our presently third condition. Sigma 1, 1 has to be equal to 0. And sigma 1, 1 is equal to the top blue equation. So 12 a3 x2 squared plus 2a5 minus 1/2 rho omega naught square a square plus x2 squared. Okay. I can, again, collect terms. This has to be equal to 0. I have 12a3 minus 1/2 rho omega naught square x2 squared, and then 2a5 minus 1/2 rho omega naught square a squared. Okay. And since this has to hold for every choice of x2, these two terms individually have to vanish. And I find that a3 is equal to essentially a1 is 1 over 24 rho omega naught squared, and a5 is 1 over 4 rho omega naught squared a squared. Okay, so that's where we are. Any questions so far? Okay, it's a lot of, let's not lose the big picture, right? The process is simple. We started with the area stress function. Equilibrium is satisfied. I'm calculating the stress just so I can look at the boundary conditions. I have to enforce compatibility at some point because I need to ensure that there's a displacement field. Once I do that, I will have, I should know exactly what these constants A1 through A5 are. And then I can go ahead and find the displacement field. Okay? So that's the stress-based approach. So now I've done a great deal, actually. And now there is one curious thing that we already perhaps realize. So I still need to enforce compatibility. I looked at boundary conditions just because I can, and they are simple to look at. And I had 5 constants, and I already found what those 5 constants are. But now I still have to enforce and ensure that compatibility is satisfied. So now I need to cross my fingers and hope that compatibility is satisfied, because that was supposed to be an additional constraint, right? If there was a, let's say, a 6 in terms, then I would be able to find a 6 by enforcing compatibility, whatever, right? But now I have everything, right? So let's see now if compatibility is satisfied. So I am going to erase this board because I'd like everything else to remain at this point. If I can keep them, I'll try. Let's work on compatibility here. Okay, so compatibility. And likewise, this is nothing to try and memorize, but we know where it came from. That's important. So in terms of the area stress function and the body force, this represents the stress. This represents the body force, the potential, right? So that's the compatibility statement. So I just need to go and take derivatives. So the left-hand side is 4 derivatives with respect to 1, 2 times 2 with respect to 1, 2 with respect to 2, and then 4 derivatives with respect to 2. And so this is 1 over omega. Now remember what omega was at this stage. Now we are recalling. Remember, I am working in a unified setting with respect to plane stress or strain. So this would be 1 minus Poisson ratio if it were plane strain, and 1 over 1 plus Poisson ratio if it were plane stress, this factor omega. Okay? So eventually I will remind you that as well. Okay, very shortly actually. So again, those are also not things that we want to memorize. Okay? It's just good to remember that we're in a unified setting. So I don't care if it's plane stress or strain. So let's go ahead and take the derivatives. 4 derivatives with respect to 1, that's easy, right? 24a1. And likewise, 4 derivatives with respect to 2, it's also easy. We call the term a3, 24a3. And then we have 2 times phi comma 1, 1, phi comma 2, 2. That term is associated with a2, but that's identically 0. So I don't need to worry about that. But let me write it anyway. So we would have a 4a2, but that is already 0, we know. Okay, so then that term, phi comma 1, 1, omega comma 1, 1, omega comma 2, 2. Omega is, right, that term. Right, that's omega. So 2 derivatives with respect to 1. So it is rho, actually it is minus 2 rho omega naught squared. That's the Laplacian of the potential. Okay, so now I have to do a little bit of board sliding. So I have an equation that is in terms of A1, 2, and 3. 2 is there, 1 is there, 3 is there. So I'm going to make use of them. So first I can use 1. This is important. So if I use 1, I can divide everything by 2. So I have a constraint, it seems, just by using 1. Okay, if I did not use anything else, compatibility enforces a constraint on A1 plus A3. So that's what A1 plus A3 has to be. Okay, and let us call this equation 4, because I'm going to eventually make use of it. Then, if at this stage I also use 2 and 3, using 2 and 3 means, okay, if I use only 1, that's a constraint on A1 and A3. But remember, I already found out what A1 and A3 are. They are 1 over 24, rho omega naught squared, whatever. So I have, right, rho omega naught 1 over 24, rho omega naught squared. I have 2 of them, so it cancels with 12. So I have rho omega naught squared on the left-hand side equals 2 minus 1 omega rho naught squared on the right-hand side. Or, okay, you cancel the rho omega naught squared. 1 is equal to 2 minus 1 over omega. Or multiply everything through omega if you like. So we would get what? Omega is equal to or omega minus 1 is equal to 0, right? Or omega is equal to 1, essentially, right? Is omega is equal to 1, I have rho omega naught square is equal to rho omega naught square. So now this is strange because omega has a value. It is 1 minus nu for plane strain. And it is 1 over 1 plus nu if it is plane stress. That means that nu must be equal to 0. Okay? Because that's the only way omega can be 1. And this is obviously too restrictive. Okay, so let me summarize what's going on here because it needs to sink in what we're trying to do here. I started with a problem-tailored form for phi. It was satisfying the simplest possible observations that I need to satisfy. Good. And then I need to, of course, also satisfy the boundary conditions. And once I did that, I found out all the constants. But compatibility needs to be satisfied because if it is not satisfied, then there is no displacement field that's associated with the stress field. The stress field is completely unphysical, right? I have to satisfy compatibility. And if I try to satisfy it with all the constants that I found out, which satisfies the boundary conditions, I find out that the only way it can be satisfied is if nu is equal to 0, right? The Poisson ratio must vanish. But I might have a material for which the Poisson ratio, let's say, is 0.3. It's not 0, which means that there is a problem here, which means that my air stress function is not good enough. The air stress function, in particular, is the correct. In fact, it is the exact air stress function if nu is equal to 0. Why do I know that? Because I satisfy boundary conditions, I satisfy equilibrium, I satisfy compatibility. But only if nu is equal to 0. So if nu is equal to 0, it's exact. Good. But if nu is not equal to 0, I have a conflict. And the conflict is twofold. On the one hand, I have the physical boundary conditions, which say that upper and right-hand side, lower left-hand side edges are traction-free. Okay. And on the other hand, I have compatibility. Okay. So if omega is not equal to 1 or the Poisson ratio is not equal to 0, I do not satisfy compatibility. But I satisfy boundary conditions, okay? If, on the other hand, I was not careful with the boundary conditions and I did not satisfy my physical boundary conditions, for instance, I could be left with, let's say, equation number 4, which is a constraint on A1 and A3, right? A1 and A3 can be chosen such that they satisfy compatibility for any choice of omega or for any choice of Poisson ratio. But then I have to sacrifice from perhaps the boundary conditions. So it seems out that I have a conflict where boundary conditions go against, let's say, compatibility. Now, therefore, I'm in a sort of a situation where I need to make a decision. And the decision comes in several layers. And let's also be careful about that. Why don't you just lay your pencils down for a second and let's look at this issue. So now that I know that I don't have the exact air stress function if nu is not equal to 0, right? So I need to do something about it. Okay. Now, what you might think of doing is perhaps you can say, well, I got the simplest possible form, right? Perhaps I could enrich phi, throw in some additional terms. Okay? What can you throw in? I already commented, I guess, right? What can you throw in? New term with the power of 6, which would add a new term with the power of 4, etc. So I keep phi in polynomial form. I keep adding terms. Now, you might get disappointed, but if you go through the same exercise of enforcing the boundary conditions together with compatibility, you will find out that all those additional terms identically vanish. In other words, their coefficients. For instance, if you had a6, x1 to the power 6, a6 will come out to be 0, etc., etc. So any polynomial term that satisfies stress symmetry, in other words, you have to have always even functions, it will always fall back to this function, which therefore retains the clash between boundary conditions and compatibility, which means that phi is not exact if Poisson ratio is not equal to 0, if I have a polynomial form. So what does that tell you about the area stress function, perhaps? It's not a polynomial function. Well, what is it? Is there a logarithm? Is there an exponential? Is there 1 over r? I don't know. Now, the point is you either go and try to find out what it is exactly, which may be very challenging, or you sacrifice. Okay? And we've done this before, actually. When we were looking at the displacement-based solution, we omitted sometimes and effects. Now, it's not clear here that there is an and effect, but eventually I will demonstrate to you that there is an and effect. And what we're now going to do is we're going to omit that and effect. Okay? Now, therefore, that eventually will boil down to, and again, maybe it's not apparent at this stage, but it will be, it will boil down to sacrificing from something in this conflict. This is not compatible with that. Okay. So compatibility is not something we can sacrifice from. I always need to have a physical displacement field from which I can find these stresses, right? So must be satisfied. And therefore, I am only left with a single choice. And that single choice is to somehow sacrifice from the physical boundary conditions in a clever manner. And I will call them, or that idea, to relax the boundary conditions. And what I mean by relax, and if you want to write anything, go ahead. I'm going to slide this board. So that will mean, eventually, the following. Here I have 3 boundary conditions. These are my physical boundary conditions. What I mean by physical is that when I look at the original problem, the physics of the problem, these are the boundary conditions as I see. And I have enforced them point-wise. Okay? In other words, I said for every x1 at the top surface, and for every x1 at the top surface, and for every x2 along the right edge, this must equal to 0. That I called point-wise. Okay? So now I'm going to relax. And now, sigma 1, 2 is already equal to 0, no matter what you do. There is nothing I can do here. A2 will always come out to be 0. There is nothing I want to do there. And now I want to recall the geometry of the problem. I want to remind you what the geometry of the problem was. Okay. So I have 2 conditions that I need to worry about, possibly 2 and possibly 3. Let's call this red. Let's call this blue. Blue was associated with the top surface. This is 2B. This is 2A. And red was associated with the right surface. Okay. Now, this edge is much thinner than that edge. So I don't want to sacrifice from this condition on sigma 2 to along this very long edge, because if I sacrifice, any error will quickly penetrate very deep into the structure and affect the stresses even already here, which is going to be something perhaps considerable, looking at the thickness of this beam. Again, maybe it's not very intuitive, but very soon with COMSOL example, numerical example, we're going to see that influence. So what I will do is I'm going to sacrifice the pointwise enforcement of sigma 1, 1 along this red edge. I will make an error, but that error will penetrate only a little bit near that edge. And if this thing is indeed sufficiently long with respect to the height, that will be an error that is constrained near this edge, so it will be an edge effect. And if I don't see the edges, my solution eventually will be perfect. Okay, that's the idea of an edge effect. So it will remind you perhaps of the, let's say, simple tension of a cylindrical bar problem that we looked at the very beginning of the, well, several weeks ago. Okay? So that's what I'm going to do. I'm going to relax this condition number 3. So instead of enforcing a pointwise form of 3, I'm going to go with a integral one. Okay? And let me show you how to do that. So for relaxation, let's reformulate. Three as, well, there is a certain, I'm going to say that essentially sigma 1,1 is not pointwise 0 here. Okay, that's going to be my relaxation. I'm going to allow non-zero values of sigma 1,1 along this edge, but such that at least physically it is statically equivalent to the forces and moments that I observe on this edge, both of which are 0. Okay? Now, let's begin with the force condition. So the force condition says that if I integrate sigma 1,1 at x equals plus or minus a along the 2 direction, it should be equal to 0. Okay? And so I have 0 equals minus b to b sigma 1,1 dx1. I have already sigma 1,1, okay, as a function of x2 evaluated at x equals plus or minus a. So this is the quantity that I need to plug in and integrate. So if you integrate, you will get 4a3 x2 cube, etc. So let me go through the integral quickly. Okay, and you need to evaluate that from minus b to b. So we would get 8ab cubed 4a5b minus rho omega naught square. I'm skipping the details here because it's fairly straightforward and doesn't add much to our discussion at this stage. Okay. So that has to be equal to 0. Now, unlike the previous form, I cannot immediately conclude that A3 has to be equal to this and A5 needs to be equal to that. Rather, here, what I have is some relation between A3 and A5. Okay, so I'm in a slightly different scenario presently. Okay. Now, you should also notice that we are enforcing static equivalence, and we, of course, also need that the moment of sigma 1,1 should be equal to 0. So sigma 1,1 x2, that will be the moment arm, minus b to b should be equal to 0, but it's automatically satisfied. Okay. It's automatically satisfied because sigma 1,1 is an even function of x2. Right? It's an even function of x2. Multiply with x2, it's an odd function. Integrate, it's an even function. Minus b to b, it vanishes. Okay? So it's automatically satisfied. I don't need to worry about that. Okay? So that's my motivation. The motivation is that I am trying to relax to resolve this conflict between compatibility and the boundary conditions. And I am relaxing sigma 1,1 condition on the right and left edges because I am observing that the body is possibly going to be thinner, or it has a smaller dimension along the x2 direction with respect to x1. Okay? And I will relax, which means, by the way, of course, I will never be able to capture a exact solution. I know already that the area stress function is not exact. I know it's not polynomial, possibly, right? So I know that I'm working in an approximate solution, but I'm putting in another layer of approximation, sort of, by relaxing the boundary conditions. I am only approximately satisfying now the boundary condition on sigma 1, 1. OK, so now we are actually in pretty good shape. We can now, and for this I'm going to do another sliding up, because just to remind you what we were doing, we can now solve for all constants in our area stress function. And well, the first one is retained, okay? From A1, from the well, I'm sorry that I want to do this again, but A2 is equal to 0 from condition number 1. Okay. From condition number 2, so this one has to do with sigma 1, 2. This one has to do with sigma 2, 2, vanishing on the upper edge. So from condition number 2, I already found out that A1 is 1 over 24 rho omega naught squared. And A4 is equal to 1 over 4 rho omega naught squared B squared. And now I'm not going to make use of 3 because that leads to a conflict with compatibility. Instead, I'm going to first enforce compatibility. So now I go up, and I know A1. I can go to compatibility equation number 4, right, just by making use of 1, right, which makes A2 vanish. And compatibility then says that you must satisfy equation number 4 between 1 and 3. I already know what 1 is. I can solve for 3. So now I satisfy compatibility for all values of omega. So that's now equation, 4, right, from that. And so we have compatibility here satisfied. And that one will give me, making use of A1, 1 over 12, 3 over 2, 1 over omega, rho omega naught squared. And now I have everything except A5, but equation number 5 gives me a relation that is to be satisfied between A3 and A5, which is associated with this relaxation. So then I go to equation number 5. That has to do with the relaxed boundary condition, and I solve for A5. Okay, I'm, of course, you may want to verify these solutions. I am fairly confident that they are correct, as long as I also write them correctly on the board. Okay, that's A5. Which comes from the relaxation of sigma 1, 1. So we have everything on the boards, actually, right? I made my observations. Simplest possible form of phi. I satisfy boundary conditions and compatibility. Compatibility is exactly satisfied. 2 of the boundary conditions are satisfied. But one of the boundary conditions on sigma 1, 1 on the right and left edge, it's only approximately satisfied. But this way, I can work with this simple form of phi, which is rather simple. And the observations were very straightforward, which immediately leads to that very simple form of phi, right? So, you know, it's area stress function construction can be non-trivial, but in this case, I should say it's not particularly challenging. Okay? And now I was able to, just by throwing in some additional observation, some additional layer of complexity, if you like, but eventually leading to a simplification on the other hand, right? So I have now all the constants. And I am in a consistent framework. I don't have any conflict of the constants with any of the conditions that I'm imposing. Okay. So now I can go and evaluate the stresses. Okay. The stresses are here, the blue equations. I'm going to substitute them, simplify them, and write what the final forms are. And I'd like to, I think, erase this board. So that's a summary of where we are so far. We have obtained an approximate stress distribution. And that stress distribution, after you make use of all the constants that we have found out, sigma 1,2 is identically 0. Sigma 2,2, if you plug in, there are some simplifications, and sigma 2,2 has, in particular, a rather neat form. Sigma 1,1, not so much, but it's not too messy either. I am sorry. I think okay, so please, I'm revising this one because I went ahead and wrote A5 once again. So let's revise that. I was wondering where all the coordinates were. Okay. There you go. That should be fine. Yes. Okay. Now, I must emphasize once again, this is an approximate solution because we have relaxed one of the boundary conditions. However, I know that as I was discussing everything, the clash appeared if the Poisson ratio was not equal to 0. That is in general going to be the case. But if the Poisson ratio is equal to 0, then in either case, plane stress or strain, so omega will take a value of 1 in both cases if nu is equal to 0. Then, therefore, this additional term that we have will vanish. Okay? And if nu is equal to 0, if you omit this term in a red box, what you are left with is the exact stress distribution, which I will demonstrate. Okay? But if nu is not equal to 0, say it's 0.3, it's approximate. Now, you should not be fooled by that red box. So in other words, it doesn't mean that this red box is the only source of error. In other words, if nu is not equal to 0, you might be tempted to think that, oh, this is the additional thing, so everything apart from this exact, in particular, sigma 1,2 in the exact solution is always 0, and sigma 2,2 has that form. No. If nu is not equal to 0, everything all of a sudden becomes approximate because I have relaxed one boundary condition. That effect influences everything else as well. So if nu is not equal to 0, sigma 1, 2 will not be equal to 0. Sigma 2, 2 will not be a function of x2 only. It will be a function of x1 and x2, etc. So I am trying to highlight the approximate nature of the solution. Okay? But although it's approximate, approximation quality increases as b over a goes to 0. Now, as usual, we also know that b over a does not have to, numerically go to 0. It just needs to be small. And in fact, often it doesn't need to be that small. We will see that, in fact, if the ratio is like 1 over 10, we have almost a perfect match between the analytical solution and the exact solution. So, in fact, when it is even 1 over 2, we're not too far off from the exact solution. So the approximate nature is, of course, there. It's always there. But it's really let me say, a very clever idea to carry out this relaxation. You sacrifice from only one thing. What you're sacrificing is from the boundary condition on sigma 1, 2. If I plug in x1 equals a, this term dies away, but this term does not. It is not equal to 0. It should be. I sacrifice from the physical boundary condition. I satisfy it only in a statically equivalent fashion. But with that, I am able to work with this approximate area stress function, which I was able to reason out of these two observations that I had. Okay, so that's the advantage that I am sort of carrying over. Okay. So we have some more time to go on this example, and we are out of time, so I will continue next time, right?